In 5.2, we're going to look at sum and difference formulas for sine, cosine, and for tangent. We're going to start off with the cosine formulas, and what I want to sort of talk about here is the purpose, one of the purposes at least, that we can have for these formulas. For one, they represent identities, so we have a way of rewriting a statement in terms of a sum and a difference of an angle into another statement involving sine and cosine. But what I want to kind of, one of the ways that we use these is that we do have some special formulas for sine, cosine, and tangent. We know that, for example, 30 degrees, 45 degrees, 60 degrees, not to mention the 0, 90, 180, 270, 360. All those have those special exact values that we know from our unit circle. 30 degrees is the same as pi over 6, so in radians, we express these this way. But they all produce those 1/2, this is pi over 3. We get those 1/2, root 3 over 2, and then root 2 over 2 when we're talking about sine and cosine. Well, a little easier to see when we're talking in terms of degrees. If I was wanting to find the cosine, for example, of 105, well, 105 can be rewritten as 60 plus 45. Or we could go the cosine of 75 degrees, right? Because 75 can be written in terms of 30 plus 45. At any rate, being that these are values that we have exact values for, the 1/2s, the root 3 over 2s, and the root 2 over 2s, we can actually find exact values for certain angles that break down into a sum or a difference of other angles that we know. So let's work through an example where we take a angle given in radians and re-express it using differences, which is what we're going to do here. Identifying and kind of recognizing these, for me, is usually easier to think of it in terms of degrees, right? And pi is always equal to 180. So if we take 180 and divide that up 12 ways, we see that that would be 15 degrees, right? And just noticing that and going, okay, 15 degrees, is there a way to use my special angles to use the difference formula? Because 15 is pretty small. We wouldn't have any ones that would be like a sum of 15, right? We don't have any special angles that are less than 15. However, there could be a difference that takes us to 15. And pi over 3 is equal to 60, and 60 minus 45, they have a difference of 15 degrees. Also, we could also do this as 45 minus 30. That would also give us something that has a difference of 15 degrees. But regardless, we're going to use pi over 3, which is 60 minus 45, to rewrite this using the difference formula for cosine. So just plugging these values in, I have cosine pi over 12, which we are re-expressing as the cosine of pi over 3 minus pi over 4, so 60 minus 45. Remember, with the cosine, we have the difference formula for cosine. We go cosine of the first angle times cosine of the second angle. And with the cosine difference formula, this is going to be the opposite. We're going to find the sum of the sine of the first angle, pi over 3, times the sine of the second angle, pi over 4. And now this is just simply a matter of using our special values that we have. Cosine of pi over 3, or 60, is 1/2. So this gives me 1/2 times pi over 4 is root 2 over 2. The sine of pi over 3, or the sine of 60 degrees, is root 3 over 2. Root 3 over 2. Multiplied by the sine of pi over 4 is the same as the cosine of pi over 4. They both have the same value, root 2 over 2. Now we can do our multiplications. This gives me root 2 times 1, or root 2 over 4. And root 3 times root 2 is root 6 over 4. And these have the same denominator, so I can go ahead and add them. If I didn't have the same denominator, I would leave it like, well, I would get a common denominator. In this case, we ended up with the same denominator, so we can combine them and write them as 1 root 2 plus root 6 over 4. Generally, that's what we want to get this down to, but of course, look at the way that the system wants you to enter your answer. If they say enter it as one fraction, then this is probably the simplest way to go as your final answer. These are simpler in the fact that we're writing it with one denominator. And of course, they're equal to each other at either side. We're just writing it as a single fraction rather than two. If we want to do a different one, let's now try doing another angle that uses the sum. And one that we mentioned there was 75 degrees. And 75 degrees, I know, is the sum of 30 plus 45. So if I wanted to find the cosine of 75 degrees is not a special angle, except for the fact that it can be expressed as the sum of 30 and 45, which both are special angles. We don't have to be as careful with the order that we put these in when it's in addition, because 45 plus 30 is the same as 30 plus 45. And the formula will work out whichever order you put those in. However, I do want to point out that in a subtraction, if I was going 30 minus 45, which is in the fourth quadrant, so not 15 degrees, which is in the first quadrant. And so we would end up with a different answer. And so we want to be careful about the order. The order really does matter when we are doing subtractions. But with addition, whether I wrote it this way or this way, we should come out with the same result. The cosine of 30 degrees is root 3 over 2. The cosine of 45 degrees, actually let me write these out first instead of just doing them. So using the sum formula, we have cosine of 30 times the cosine of 45. We add an addition here, so we're going to put a subtraction here, and then do the sine of 30 times the sine of 45. Degrees. All right, cosine of 30 we know is root 3 over 2. Cosine of 45, root 2 over 2. And since we have an addition, we're going to subtract and find the sine of 30, which is a half, times the sine of 45, which is root 2 over 2. And so this gives me square root of 6 over 4 minus root of 2 over 4. Putting that as one fraction, we get root 6 minus root 2 over 4. And that is pretty much simplifying as much as possible. And we can look at this also, know that root 6 is a higher value than root 2. So when I subtract these two, I am going to get something that is positive, right? The only way we could get negative here is if these two were reversed. That would put us in a negative territory. And here, same thing. Cosine of both of these angles is positive. They're both in the first quadrant, 15 degrees and 75 degrees. So cosine is positive in the first quadrant. Both of these are giving us positive results. So I want to bring us back to one of the things that I talked about earlier, just visualizing the relationships that we have here, because you'll notice that the sine and cosine kind of switch spots there, whether we're talking about 30 degrees or 60 degrees. So I'm going to draw approximate 30 and 60 degrees. I'm going to try to draw a unit circle here so that they are about the same radius of 1. And so we have 1 here and we have 1 here. So this is 30 degrees and this is 60 degrees. We know that at 30 degrees, remember, sine and cosine are just points on your unit circle, cosine being the first. You can see that the x value is close to 1. Well, the root 3 over 2 is greater than the other value, which is 1/2. They kind of switch between these two. And you can see at 30 degrees at the y-axis, we're about halfway. My drawing's a little imperfect, but about halfway between 0 and 1. So the y value is 1/2, the x value is root 3 over 2. Once we go to 60 degrees, the opposite happens here. The x value is about 1/2, so the cosine, and the y value is at root 3 over 2. That's a visual I always like to use when I'm trying to picture, okay, if I just lift it up a little bit, I can see the x is just a little bit short of 1, but y-wise, we're about halfway up there. It's just kind of the way the circle, the arc there, where that puts us. Also, I want to point out that because these have that, the sine and cosine have that relationship on the unit circle, when I go 60 degrees, this is the same angle I would get if I go 90 minus that 30. So 90 minus 30, so this here would be 30, give us that 60. So there's this relationship between where this is in relation to the x-axis and where we are in terms of the 90, the y-axis. Also, if I go 30 degrees from the x, I'm now at 90 minus that, so 90 minus 60, which also gives me that 30. So, just to point that out, I want you to keep that in mind as we look at these identities on the next page here. If you can visualize that 30-60 degree relationship in relation to 90, it'll help make these a lot clearer. In fact, that relationship that we just saw is basically described here, where V is our angle. So the cosine of 90, or pi over 2, minus an angle will be equal to the sine of that angle, right? Because they switch spots, right? So V is like a 30, 90 minus 30 is 60, and that's the same value we would get if we took the sine of 60. And those go for both sine and cosine. Again, they just kind of switch spots there in terms of their results. If I go 90 minus this angle, I'll have, and take the sine of that, it's the same thing as I would get of cosine of that angle. And because of that relationship, we know that that will hold true also for secant, because cosine and secant have that inverse relationship. Sine and cosecant have that inverse relationship. And as well, tangent and cotangent will end up having that similar relationship because tangent is simply made up of the ratio of sine over cosine, and tangent is the cosine over sine. So this works whether we express it in radians or we express it in degrees. These relationships hold up and can be helpful for us when we're looking at other scenarios. just to prove this, let's take a look at tangent. We can at least prove this one. Some of the other ones are a little more difficult to prove, but since tangent is made up of sine and cosine, it's more easily redescribed, right? So tangent of any angle is equal to the sine of that angle over the cosine of that angle. Sine over cosine. The angle in question here is pi over 2 minus v and pi over 2 minus v. Right, so we just all we are is putting that angle that's being described in here and expressing it that way. Looking at these individually, I know that the sine of pi over 2 minus v is actually equal to the cosine of v. And the cosine of pi over 2 minus v is equal to the sine of v. And cosine over sine is equal to cotangent. That's what cotangent is being described as. And so we can see it's a very simple proof to show that this identity actually does work. We also have sum and different formulas for sine. They're very different than the ones for cosine, but we can definitely see some patterns here as we examine them, patterns that we can kind of remember, which help us to commit them to memory. Where they differ, one thing you'll notice is that they always start out with the sine of the first angle. So sine of the first angle is always the first, no matter if it's a sum or a difference. It's the sine of u, but then we take the cosine of v in both. And then since we've already done the sine of u, what's left is to take the cosine of u, and then, which we haven't done yet, the sine of v. The sum has a sum here, so the signs actually match up. But one thing to remember is, like, do we take the sine of u first or the cosine of u? Since they are the sine formulas, we take the sine of u first, whichever we have written here first. Let's do a similar thing that we had before. Let's find the sine of one of the angles that we had previously. Let's take the sine of pi over 12. So with pi over 12, we know we can write that as the sine of pi over 12 is 15, so root 3 minus, not root 3, but pi over 3 minus pi over 4. So 60 minus 45. With the sine, we have the similar signs. So, and I always take the sine of the first. So we go sine of pi over 3. And with the sine thing, we take the cosine of pi over 4. The signs are going to match up here. So then I haven't taken the cosine of pi over 3. So now I take the cosine of pi over 3 times the sine pi over 4. Simplifying these out, sine of 60 degrees is 1/2. Oh, I'm sorry, I have that backwards. That would be root 3 over 2. The cosine is square root of 2 over 2. And the cosine of pi over 3, 60 degrees, is 1/2. Sine pi over 4 is root 2 over 2. So we end up here with root of 6 over 4 minus root 2 over 4. And so that gives me the root of 6 minus the root of 2 over 4. That looks familiar, doesn't it? Let's go back to the other screen that we had. This was the same thing that we got back here when we took the cosine of 75. Notice that 75, let's draw that in, would be right about here. And guess what? This is 75 degrees. That leaves us with 15 degrees here. And this was the cosine. So we're saying the cosine of 75 degrees was equal to the sine of pi over 2 minus 15 degree, or pi over 3. Okay, I'm actually, let me go back here. This is the same thing as 90, because I want to put it in degrees, minus 75. Right? The sine of 15 degrees was equal to the cosine of 75 degrees. That's our identity at work here. The cosine, or we found the sine, right? So the sine of 15 degrees was equal to the cosine of 90 minus 15, which is 75. And vice versa, the sine of, or the cosine of 75 was equal to the sine of 90 minus 75, which is the sine of 15. So you see how those cofunction identities produce the same result. That's just the function of a identity. All right, so here we're actually presented with a problem that at first seems like, okay, we could maybe do a sum or a difference. This kind of follows into that. But what we're presented with is the sine of 63, cosine of 27 plus cosine of 63, sine of 27. And we want to find an exact value, meaning we don't want to use our calculators to do this. How do we do that? 63 and 27 are not special values that we have answers for. Nor can we come up with really any kind of way to add two angles that are known values to get 63 or 27. However, what they've presented us with here is in the sine, the sum of two angles, taking the sine of the sum of two angles. And so if I rewrite this, kind of undoing it, right? This fits into the formula for the sum of two sine of u plus v. We know the sine of u plus v is equal to the sine of u times the cosine of v plus the cosine of u, make that look more like a u, times the sine of v. And so with the 27, let's just rewrite this. We know that since it's in that form, this will be equal to the sine of 63 plus 27. This is what I had, sine of 63, cosine 27, cosine 63, sine of 27, right? So I'm kind of undoing it or using the formula in the other direction, because we might notice that 63 plus 27 gives us something similar to 60 plus 30. It comes out to be 90 degrees. And the sine at 90 degrees, the y value, when we've taken an angle to 90 degrees, is 1. And so that we can simplify this whole thing and know, without using our calculators at all, that that would have a value of 1. Look for little patterns like that in some of your problems. All right, in this problem, we're given some partial information that we need to fill in the blanks for. And our goal is to find the sine of u plus b. We're given some clues up here. We're not told what u and v are, but we're told that the sine of u is negative 3/5, and the cosine of v is 12 over 13. We're also told what quadrants they're in. U happens to be in the third quadrant, and V looks like it's in the fourth quadrant. looking at the signs of my outcomes, I know that u, which we're taking the sign up, we're getting something negative. Well, everything is negative except for tangent in the third quadrant. And cosine was positive. And of course, yes, cosine is positive in the fourth quadrant. So let's write out what we're trying to find here, which is the sine of u plus v. I know this is equal to, again, we're doing the sine here, so sine of u times the cosine of v. We use the same symbol there. We add and then do the cosine of u, sine of v. Let's fill in what we have so far. We were given the sine of u, so I know this is negative 3/5, but we do not know the cosine. Oh, we do know the cosine of v, sorry. We know the sine of v and we know the cosine of v. So this is times 12 over 13. What we don't know is the cosine of u and the sine of v. So now we need to do some detective work here. I know that u, I don't necessarily need to find the formula. I just need to know what the cosine and the sine would be for that. But u is in the third quadrant. So I'm going to go ahead and draw this out as a triangle using that ratio that we have there. Third quadrant, we were told that the sine of u was negative 3 over 5. So that would be here, negative 3 and 5. And so really what I need to find is what's this value here. I'm just going to put it as x. We know that x squared plus negative 3 squared would give me 25. X squared plus 9 is 25. And let's see, we have one of our special triangles, x squared equal to 16. And so x is equal to 4, the square root of 16. This is a 3, 4, 5 triangle. So I may not know what angle would give me that, but I do know that this side here would have a length of 4. The other one is in the fourth quadrant, and again, I'm not drawing these to scale, but we're told that the cosine is 12 over 13. And so that would be adjacent over hypotenuse. They're positive, which makes sense because this is going in a positive direction, so that's a positive 12, and the hypotenuse is always positive. What we need to figure out is that third side. The 13 is my hypotenuse, so 13 squared will equal 12 squared plus, we'll put this as y squared. So 169 is equal to 144 plus y squared. And then subtracting 144 on both sides will give me 25 equal to y squared. So we know that y is equal to either positive or negative 5. Oops, not square root of 5, but just 5. And I know in this case it has to be negative 5 because the y would be a negative. We're going down. So that's negative 5 over 13 would be the sine of that angle. So this is v, and this is u. So working these out, we're going u here, which would be the same as just the reference angle that I had drawn in there. So cosine of u is this angle over here. This actually, is a negative 4. I mistakenly wrote positive 4. But when we take the square root, we actually get positive and negative. But in the context, this is a negative x. And we're in the third quadrant. Both cosine and sine are negative in that quadrant. So that gives me adjacent over hypotenuse, so negative 4 over 5. Multiplied by the sine of v, which sine is opposite, so negative 5 over 13. And then we can go ahead and carry these out. Negative 3 times 12 is negative 36. So this is negative 36 over 5 times 13, 65. And this would give me positive 20, negative times negative, over 65 as well. And negative 36 plus 20 is negative 16 over 65. Checking out, do they have any common factors? 16 is made up of a bunch of 2's, and 65 has no 2's in them. And so we can see that this is my final answer here for the sign of the sum of u and v. Tangent also has a sum and difference formula. And again, let's kind of examine it in terms of patterns we can notice. We have a u and a v. We go tan u, tan v. When we're adding, we're adding. And then on the bottom, we go 1 minus tan u, tan v. In fact, on the bottom of both of these, we have that 1 tan u, tan v thing, but they are opposites. So here my plus lines up with that plus, and this is the opposite. Here this difference lines up with that difference, and then that ends up being the opposite of what I had on top. So that's one way you can remember that. We have this identity that's presented with us, to us here, and we can use that formula to verify this. So our goal is to make it look like negative tan x, and we have the subtraction here. So using that, we're going to find the tan of pi minus, we're going to have the same sign there, tan of x. And then on the bottom, we are going to have the opposite, 1 plus tan pi tan x. So what is the tangent of pi? Well, the tangent of pi is 0. We'll look at our little chart. It's one of the special things. It gives us tan is sine over cosine. So sine over cosine. And remember, sine at 180 degrees or pi is 0. So that gives me 0 over negative 1, which is 0. And so this is going to become a 0. This is going to become a 0. Simplifying that out, that would be 0 minus tan x. And on the bottom, I would have 1 plus 0 times tan x. 0 minus tan x is just negative tangent of x. 1 plus, this product comes out to be 0, so we end up with 1 plus 0, or 1. And so therefore, we can see that this identity actually does work. The tangent of pi minus an angle is equal to the negative tangent of that angle. So all of these connections between sine, cosine, etc., all these different identities we have, we've looked and explored them. This is just another tool in our toolbox to use in either verifying identities or finding exact sums and differences of particular angles that we're after. All of these tools can be used in a lot of different ways, so that's what you're going to explore in this section.